All right, so welcome back. First of all, just a reminder, I know I've said this several times, but just to put it up one more time. If you have any questions about anything we went over yesterday or anything that we're going to go over today, you can always email those to me at my email address, which is written right up here. So feel free to send me an email if you have any questions over what we're going over that can't wait until Monday. So anyway, we left off talking about some chemistry stuff, and so now we're going to pick up with models of atoms. If you're looking at your review, we should be off the first page for sure. I'm actually not sure exactly where we are. It's the one where it asks, like, for the Bohr model. We just finished talking about the finding number of protons, number of electrons, and number of neutrons. So anyway, models of atoms. We talked about several in this class, but the one that we're going to focus on, which is the common, or not the common one, the current one, is what's called the Bohr model. Okay, this is named for Niels Bohr, who is the scientist who basically came up with this idea. And the Bohr model was very important because it added a little bit of a detail to the model of the atom that we had not yet known about at that point, which is the idea that electrons exist in energy levels. So the Bohr model uh, basically is including electron energy levels. Electron energy levels. Or, you know, sometimes those are called orbitals. Okay? So if we're going to look at the model, the Bohr model of the atom, it's pretty simple. In the center goes a circle. Um, that circle, that represents the nucleus. Okay? And then around the circle are going to go the electron energy levels, the orbitals. Okay? So around that circle go these electron energy levels, and those electron energy levels are going to have little dots on them that represent actual electrons. Okay? So the little lines, those are electron energy levels. Okay? The dots are electrons. Okay? And then let's say that this one in particular has 10 protons. You know what? I can do this a little better. Bear with me. There we go. Oh no, I was doing everything so small. Don't really need to. I got plenty of space. So 10 protons. 10 protons means if we're neutral, we're going to have 10 electrons, because in a neutral atom, protons equal electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, Okay, so that center one, again, is the nucleus. The outer ones are the electrons, and the lines are the electron energy levels. Okay. Inside the nucleus, you have the number of protons. Now, the reason we need the number of protons is knowing the number of protons will tell you what atom you're actually talking about. So 10 protons means we're talking about element 10, which is neon. So this is neon right here, a neutral neon atom. So we have 10 protons and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. Same protons and electrons. That's what makes it a neutral atom. The other thing to remember about the Bohr model is your electron energy levels fill up in order. What I mean by that is they're going inside to outside. So we're going to start by filling up your innermost energy level. This is, so like this one right here, that's level 1. And it holds 2 electrons. We then go out to here. This is level 2. And it holds 8 electrons. And this information I'm just getting from, remember on your periodic table, you should have the notes noting exactly what, all the different things on the shape of the periodic table means. And the number of electrons will fit in a given energy level is given by the number of atoms in, or number of elements in a row. So row 1, remember rows are the horizontal ones, so going this way. So your row 1, the only 2 elements in it are hydrogen and helium. Hydrogen and helium, 2 elements, so level 1 holds 1, 2 electrons. After that first level, if you go down to the second row, so the second little thing going this way, the second one going that way has 8 elements, meaning that the second energy level holds 1, 2, 3, 4, 5, 6, 7, 8 electrons. Same with the next one. It's got, again, has 8 electrons in row 3. So energy level 3, which isn't in neon, but if it were, energy level 3 would hold 8 electrons as well. So that's just a quick overview of the Bohr model of atoms. Okay, so next we need to talk about some special cases of atoms. So first we'll talk about isotopes. So an isotope is an atom of an element with a non-standard mass. What that basically means is it's an atom of a particular element that has a different mass than what you would normally expect. So the example that we used yesterday was oxygen. Oxygen usually has a mass of 16. However, if you look at the atomic mass on the periodic table, you'll see that the atomic mass is given as 15.999. That's because almost all oxygen atoms have a mass of 16. However, every once in a while, there's an atom that has a slightly smaller mass, a little bit less than 16, like 15. Okay, it's got less neutrons. What that would mean is that that atom that has the different mass, the atom that has a mass that is not 16, so it's non-standard, it's not 16, something else, that would be called an isotope. So, to be an isotope, atoms must have same number of protons. So same number of protons means it's the same element, because it's got to be atoms of one element. So same number of protons means same element. And so both these things must be true. So same number of protons and, okay, it's got to be both, and different number of neutrons. Okay? Because remember, in order to be an isotope, that means they have to be the same element. So same element is going to be same number of protons. And a different mass. So the only way to change mass, if protons are the same, is by changing neutrons. So same protons and different neutrons, then you're looking at an isotope. Ions. An ion is an atom with an electric charge. So we have an electric charge on ions. Ions, the only way to get an ion is have the number of protons and number of electrons not equal. Okay, so if protons do not equal electrons, then you're looking at an ion. Okay, so ions can be positive or negative. Okay, positive or negative. If it's a positive ion, we call that a cation. And if it's a negative ion, we call that an anion. Okay, so remember, stupid way to remember it is cation. Cats have paws. Cats have paws. Cation is positive. Anion is negative. Okay? Another thing to remember is this very simple idea, which is if you're the same column, you're looking at the same chemical properties. Now, if you're wondering why same column, same chemical properties, remember column, we're talking about up and down here. So the vertical relationships on the periodic table. So same column means same number of valence electrons. Okay? So same number of valence electrons is going to give us the same kind of chemical properties, so the same reactivity, the same bonding behavior for the most part, and simplified, very simplified. We're going to see same basic chemical properties shared within a column. Okay, that is all because of the valence electrons. Valence electrons are determined by the column. So the periodic table is set up so that elements with the same number of valence electrons are given in the same column. So if you're in the same column, same valence electrons, same chemical properties. So here is a lovely periodic table. And on this periodic table, on your review, I've asked you to do two things. I want you to first label the valence electrons. I also want you to label, oops, so I want you to label the oxidation number. Okay, so we also want the oxidation number. So what I'm going to do is I'm going to do the valence electrons on mine in red. I'm going to do the oxidation number in green. So let's start with valence electrons, because valence electrons is the first one that we learned. So valence electrons are going to be determined by column. And so we're going to start over here. These guys have 1. Our next column has 2. We skip the transition metals, so we're not going to worry about these guys for now. Skip the transition metals because they have variable valence electrons and oxidation numbers. And we're going to come over here. So, well, they have variable oxidation numbers. We're next going to come here. We have 3, 4, 5, 6, 7, and 8. Now, remember, helium has 2 protons and 2 valence electrons. Okay, so helium is a special case. All these other ones have your 8, your full. So remember, 8 really means full valence shell. Now, if we want to get oxidation numbers are the charge that atom will take on after it goes through ionization. Ionization is either gaining or losing electrons to form an ionic bond. So when we are doing ionic bonding, we need the oxidation number because that will tell us how many electrons an atom is going to tend to gain or lose, which will help us figure out how many of each particular atom you need to make a balanced chemical equation. Anyway, so oxidation numbers also follow a pattern because oxidation number is related to the number of valence electrons. It also is going to follow this column pattern, so this up and down pattern. So we'll start over here, and our first one is +1. Then we go to +2. Over here, +3. Right here, plus or -4, -3, -2, -1, and 0. So remember, again, oxidation number is the charge of the atom after it goes through that ionization process, either gaining or losing its electrons in order to form ionic bonds. So these ones over here are metals, right here. All of our metals have positive oxidation numbers. What that means is that our metals are going to be, for the most part, giving up electrons. If you lose electrons, you become positive because you're losing negatives. So you lose negatives, you give to charity, giving away. That's a nice thing, a positive thing. So you're going to end up with a positive oxidation number. These guys over here, the nonmetals are gaining electrons. They're stealing. Remember we said stealing is bad, so stealing is negative. So if you're stealing electrons or you're taking away electrons, you're going to end up with negatives. Okay. This row is kind of our special case. It's plus or minus 4 because it can kind of go either way. Because it's no easier or harder to gain 4 electrons than it is to lose 4 electrons. It's kind of a wash. So it can go either way. So anyway, the periodic table at this point is going to become very handy for the rest of the stuff we're going to do on this review. So it'd be very smart to keep a copy of this handy. So how many total atoms is the first thing we're going to have to talk about. So we're going to have to answer questions about how many total atoms in different compounds. Okay? So let's pull those up and take a look at it. So the first one we're going to look at is NH4Cl. So we have this NH subscript 4Cl. So taking a look at this, we need to first determine how many atoms there are of each individual element. So N, we have one of them. H4, that's 4 atoms. Cl is 1. If we add these together, that's going to be 6. Okay. Next one is H2O. So for H2O, H2 is 2, O is 1. If you add those together, 2 plus 1, that's 3. And then finally, Mg, and then we have a parentheses, C2, H3, O2, close the parentheses, and then a 2. So this one's a little bit trickier, but we can knock it out no problem. So Mg, we have one of them. Now we've got C2H3O2, but the whole thing we have 2 of. So that means we have to take everything inside here and multiply it by 2 because we have it twice. Okay, so we're going to take C2 times 2. So C2 is 2. 2 times 2 is 4. H3, H3, so that's 3. 3 times 2 is 6. O2, O2 is 2. 2 times 2 is 4. So we add all these together. 1 plus 4 plus 6 plus 4, that's going to be equal to 15. Okay? So again, all we're doing is just basically adding up the subscripts. If there is no subscript, you can assume that it's a 1. So 1 plus 4 plus 1 is 6. 2 plus 1 is 3. 1 plus 4 plus 6 plus 4 is 15. All right. So next, let's talk about our types of compounds, and then we'll actually do some naming. So first, types of compounds. Ionic. So ionic compounds are made up of a metal and a non-metal. A metal and a non-metal being bound together. The rules are pretty simple. You just say the metal, then non-metal with the end changed to "-ide". So it's going to be whatever "-ide". Okay, so like oxide or sulfide or chloride, fluoride. Okay, so it's going to change the end of the thing to "-ide". Covalence. Covalent compounds are made of 2 non-metals. Okay, so a metal, non-metal and a non-metal. On these ones, you're going to use the prefixes. Okay, you're gonna have to use prefixes. The prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Um, I will provide those to you on the test, so you don't have to worry about, coming up with those off the top of your head. I will make sure those are available to you. But anyway, you're going to use prefixes, and then you're also going to end in "ide" still. Now, when you're using prefixes, one little, uh, I guess, I don't know, it's not really an exception. It's just one thing to keep in mind is just that when you're using prefixes, don't use mono on the first word. So what I mean by that is like CO, that's not monocarbon monoxide. It's just carbon. And then now the second one, you use monoxide. Okay, you don't have to use mono on the first one. So it's just carbon monoxide. Okay? Polyatomic. Polyatomic is anytime you have three or more elements. So if you're seeing three or more elements, that is polyatomic. Poly means many. So if you got three or more, it's going to be polyatomic. So for that one, it's pretty easy. Again, you have to look up the polyatomic ion. So look up the polyatomic ion and cation, which is the first word, is named normally. What that means is you don't change how you say it. So like if you have like calcium sulfate, CaSO4, like this. SO4, this guy right here, that's sulfate. So the cation, the first word, is just calcium. So you say calcium, and then this is sulfate. So the name would be calcium sulfate. Okay? So using that information, we can kind of plug these in, see if we can figure these out. So our first one is CO, which I use as an example. CO is going to be a covalent compound. If it's covalent, we're going to use prefixes. So the name would be first carbon, because we don't need the mon, so just carbon monoxide. Okay, so we got oxide, and then mono is our prefix. So monoxide. Next, we've got BES. So to do this one, you look up what we got. So Be is beryllium. That is a metal. That's a metal. Okay. S is sulfur. That is a nonmetal. A metal and a nonmetal means this is ionic. So if it's ionic, you just say the first one. So Be is beryllium. And then S becomes sulfide because it's sulfur. Sulfur gets changed to sulfide. Yeah. Next, we have CaSO4, which is another one we use as an example. So CaSO4. This is 1, 2, 3 different elements. That makes it polyatomic, which I guess we did as red. So for polyatomic, we just need to say the first one, which is calcium. And then the second one, SO4, this guy right here. SO4 altogether is sulfate. You just got to look that up on a polyatomic ion chart. Next, KCl. So KCl, K, potassium, metal, Cl, non-metal, metal and non. It's ionic. It's ionic. Once again, you say the first one, so potassium. And then the second one, chlorine becomes chloride. Last one, K2O. So K, potassium again, still a metal. O, oxygen, non-metal, so that is also ionic. Ionic does not use prefixes, so that K2 doesn't matter. It's still just potassium, because we don't use a prefix. So potassium, and then O, oxygen, becomes oxide. Okay, so hopefully you're fairly comfortable with these at this point. So next, oxidation numbers. So oxidation numbers are, again, we've said this before, but just to reiterate, oxidation numbers are the charge after electrons are gained or lost. So what this means is after we gain or lose electrons, we're going to be left with the charge. And so, for example, if we have an oxidation number of +2, so like we have Mg2+, that means our overall charge is +2. +2, in order to be positive, it means you had to lose negatives. You had to get rid of negatives. So that means you lost 2 electrons. You lost 2 negative charges. That means you're going to be left with a surplus of 2 positives, giving you an overall charge of +2. Okay? Likewise, Li1 plus. If you're +1, that means that you have a surplus of positives. So again, you have lost negatives. So lost 1 electron. We can't gain positives, so you can't do like Li plus 1 is gain 1 proton, because if you gain a proton in a lithium, it's not a lithium anymore. That changes the identity. So it has to have the same number of protons. Next, O2 minus. So 2 minus means we have a negative charge. So we're more negative. That means we have gained negatives. So we've gained 2 electrons. Then our last one is a polyatomic ion. So we got CrO4 chromate. And that has an ionization oxidation number of 2 minus, meaning also we have gained 2 electrons. Because there are 2 minus, that means we are 2 more negative, more in the whole, 2 minus. Okay, the octet rule. So the octet rule is basically, if you put it very simply, it's the idea of if I ate, I full. I know it's really bad grammar, grammar, but you know, it gets the point across. So the idea basically is 8 valence electrons uh, is a full valence shell, and then atoms are stable with a full valence shell. They're stable and happy when they have that full valence shell. That's what they're looking for. That's the goal. Okay, so when atoms bond with each other, what they're trying to do is get that 8 valence electrons, that octet, to get that full valence shell. If they get a full valence shell, they're stable. They don't need to go through any more reactions. So, phase changes. If we don't talk about phase changes, this is change from one phase of matter to another. So, some things to think about here. We could have freezing. Okay, so freezing for water, that happens at 0 degrees Celsius. Okay, and that is going from liquid to solid. It is a loss of energy, a loss of heat. We can also talk about boiling. Boiling, once again, we'll focus on water because that's kind of our example substance. So water boils at 100 degrees Celsius. And that's transfer, or not transfer, the transition from liquid to gas. So we're adding energy, we're getting more energetic, going from liquid to gas. Okay, now the reason we talked about phase changes is we use that for our ice cream lab. So in the ice cream lab, we were looking at phase changes and we were able to do a freezing. We took liquid cream to solid cream, and we did that by removing energy. We removed energy with ice, and we were able to remove ice because of what's called freezing point depression. So the review asks you to describe freezing point depression. So freezing, E, E, Z. Let's start over. It's rough. This word is going rough. Let's try again. F, R, E, E, Z, I, N, G. So freezing point depression. What this means is you basically add a solute to lower the freezing point. What that means is that the substance, whatever it is, so in this case we used ice. So the ice actually froze at a lower temperature, meaning that our ice-water mixture was able to get colder than it would normally. By being able to get colder, we were able to actually freeze the cream and end up with the ice cream. If you would put your bag of cream into just regular bag of ice, you would not have gotten ice cream because it wouldn't have been cold enough. So by adding that solute, we use salt. By adding that solute, we were able to actually depress the freezing point, which lowered that, made our mixture colder, and allowed us to make the ice cream. Okay? If we hadn't added the salt, you would not have ended up with ice cream. We would have just had a cold bag of milk, and nobody likes a cold bag of milk. So, next, physical versus chemical change. This was like kind of the last topic we talked about. So physical versus chemical change. Physical change. A physical change changes the appearance of a substance. Okay, so it changes what something looks like. So examples would be like I have a piece of paper and I wad it up, or I tear my piece of paper in half. Or I take liquid water and I boil it and turn that liquid water into water vapor, into water gas. Okay, the key thing here is after a physical change, the substance is still the same thing. Okay, so you might have changed how it looks, but you didn't change what it is. So if I take a piece of paper and I wad that piece of paper up, that doesn't mean it's not paper anymore. It's still paper. It just has undergone a physical change. It's in a different form. It looks different. It's still paper though. Chemical change is different. So chemical change, this changes the identity of the substance. So what that means is you basically end up with something new. Okay, so we end up with something completely new. It's no longer what it was. It's gone through a chemical change. It's something new. So the example we did in class was the fire. So I took that same little piece of paper that I wadded up for a physical change. That piece of paper, I lit it on fire, so I underwent an oxidation reaction. I set it on fire. And at the end, what was left over, those ashes, go away. What we are left with was something completely new. Okay, ash was not paper. Cancel the shutdown. Okay. Left with something completely new for a chemical change. So, next, balancing equations. If we want to balance equations, let's see, I think we're just about there. Yeah. Yeah. So balancing equations is the last thing. So in order to balance equations, first thing we need to remember is the law of conservation of mass. So the law of conservation of mass basically says mass cannot be created or destroyed. What this means is everything at the beginning has to equal everything at the end. So before has to equal after in any chemical equation. So before has to equal after. So we got a couple examples of equations to balance. So our first one is Cu2O plus C is going to yield Cu plus CO2. So in order to do this, first thing you want to do is you want to figure out what you have on each side. So on this side, I've got Cu, I got copper, I got O, oxygen, and I got C, carbon. Okay, on this side, again, I have Cu, I have O, and I have C. So let's do an initial count and see how much of each thing we have on each side. So Cu, I have Cu2, that's two of them. I have O, just one of them. and I have C, just one of them. On this side, I have Cu, one of them, O, it's O2, so I have 2 of them. And C, again, I have 1 of them. So next thing we need to do is add coefficients to balance. So let's work on C. Let's work on O first. So we have 2 O's over here. We have 1 O over here. So I'm going to make this a 2. So now we distribute this coefficient to get a new count. So we have 2 Cu2s, so 2 times 2. That is now 4. 2 times 1 O. That's now 2. So our O's are good, but now our Cu's are screwed up. So if we put a 4 right here, 4 times 1 Cu is 4. So at this point, we have 4 and 4. We have 2 and 2. And we have 1 and 1. So all of them are the same. That's a balanced equation. That's good to go. Okay, last one. We have Na plus HCl, hydrochloric acid. It's going to give us H2, hydrogen gas, plus NaCl, which is sodium chloride salt. So anyway, on this side, again, we have Na, we have H, we have Cl. On this side, we still have Na, we have H, we have Cl. So on this side, we have 1 Na, 1 H, 1 Cl. On this side, we have 1 Na, we have we have 2 H's, we have 1 Cl. So let's balance this. Over here, we have 2 H's on this side, so let's make 2 H's on this side. So I'm going to make a 2 there. That's going to change that 1 into a 2, because 2 times 1 is 2. It's also going to change this Cl into a 2. Now Cl is not balanced on this side, so if I put 2 here, 2 times Na makes that a 2. 2 times Cl makes that a 2. And then finally, our Nas aren't balanced, so if I put a 2 here, 2 times Na is 2. It won't change this. So that means at the end, I've got 2 Nas on both sides. I've got 2 H's on both sides. And I've got 2 Cl's on both sides, meaning that I am balanced. So anyway, that wraps it up. That is the full final review. Again, if you have any questions or you need any more help, please make sure you're sending me an email or send me an Edmodo message, and I will get to those as soon as I can. And I will also be available, obviously, on Monday all day. We will have one more day review to make sure that everybody is good to go, so that when we take the test on your final day, everybody's ready to rock and roll, and we do really well to finish off the semester. So anyway, thanks a lot for paying attention and listening, and anyway, have a great weekend, and I will see you on Monday.